so I think we can slowly continue. Welcome back. Our second speaker for today is Volker Bach, and he will speak about beyond the Van Hove timescale.
Yeah, thank you very much for the introduction, and thanks to all the organizers for giving me the opportunity here to report on research results in this workshop, which are related to renormalization, as you will see during the talk. So let me start here. I will change during my presentation between a Beamer and Blackboard a little. So that's why I erased the announcement there. There was an announcement about shifted talks. All right, so what I would like to tell you about is joint work with Jacob Möller in Aarhus and Matthias Westrich, who's working for Allianz Insurance now. So he left academia. And what we would want to, we pose the following question. I mean, let me mention this as a guideline. Namely, we would like to have an effective generator for the evolution. Suppose we have a Hamiltonian which generates the evolution of a quantum system, and we want to relate this for large times to some effective and simpler Hamiltonian that acts, for example, on a smaller subspace of the original state space, or has a simpler structure, or both. So this is for times that are very large, and in fact times that are large even compared to the inverse squared of the coupling constant here, and that is what is in the title meant by the Van Hove timescale. So this we study concretely on a model which is simple yet non-trivial, of an atom, an L-level atom coupled to a scalar quantum field. So if we have a two-level atom, if L, capital L, is 2, then the model I'm discussing here is known as the spin-boson model. And this is I mean, this is used very much in the theory of quantum optics to model lasers or qubits, qubits coupled to external quantized fields, say. And so this model has clearly has a relevance for practical applications in physics. And yet it is simple, and I can describe it here in short terms completely. I mean, in a few minutes completely. So it's defined. I mean, it's a quantum mechanical model. So we are defining it by specifying a Hilbert space, whose vectors are the state vectors of the system, and a Hamiltonian that generates the time evolution by Schrödinger's equation. The Hilbert space in this case is the joint Hilbert space of the atom, the L-level atom. So that's the CL here, times the Fock space that carries the scalar field. So here you see FB is the boson Fock space over a field whose one particle space is the space of square integrable functions in 3 dimensions. And the Hamiltonian of the system is a self-adjoint operator, as usual. Here is given in the perturbative form. So I'd like to have a Hamiltonian here, which is already a simplification from first principles. I'd like to have the Hamiltonian to be of the form H0, the unperturbed Hamiltonian plus a perturbation coupled in by a small parameter g, so which I choose to be positive just for convenience. And W is the interaction that I will tell you about now. So let's see in more detail what this model looks like. Again, the Hamiltonian is of a perturbative form, H0 plus G times W. And the unperturbed Hamiltonian is the sum of the two energies of the subsystem, the two Hamiltonians of the atom and the photon field, if we think of this quantum field as the photon field. So their Hamiltonians basically are added up, and if we take this H0 to generate the time evolution, then the atom evolves and the field evolves, and they basically don't know about each other. So it's it would be a non-interacting system that is modeled by H0. The atom Hamiltonian is an L by L matrix, so after a unitary transformation, if necessary, we can take this Hamiltonian to be a diagonal matrix with the atomic energy levels on the diagonal. And I just order them and assume, and that's an important assumption here, that these eigenvalues are simple. So hydrogen, for example, is not included in this example here, so to say. Okay, so the atom Hamiltonian, if we have L equal 2, is, in other words, is an eigenvalue E1 and E2, 0. It would be a 2 by 2 matrix, like that. Then comes the interaction and the photon Hamiltonian first, sorry. So we have here massless field. The dispersion of the quanta here is k absolute value. And I write this down directly in second quantized form. So the A star of k and A of k are boson creation and annihilation operators at momentum k, and they fulfill the canonical commutation relations as usual. So maybe I just write them down. So the commutator of A, k, and A star of k prime is delta k minus k prime times the identity. And this is understood in the sense of operator value distribution. So we have to integrate here k and k prime against suitably regular test functions, and then this relation makes sense as an identity on Fock space of linear operators. And all other commutators vanish, and furthermore, the annihilation operator annihilates the vacuum. So for all k, A of k applied to the vacuum vector, omega is 0. Omega is the vacuum vector. Okay, so then we have the interaction W, and it is, for simplicity, given here in a kind of as a product of two multiplicative factors. So M is a L by L matrix that can be thought of as the orbital matrix of the atomic orbitals, and which they overlap through the interaction, let's say modeled by a dipole interaction term or something like that. And then we have creation and annihilation operators again here, where G is the function specified below, down here. So G is a function that is regular both in for large k, so in the ultraviolet region, it's cut off at scale capital lambda, and also it is infrared regular. Here in 3 dimensions, this means that the singularity at k equals 0 is milder than k to the minus 1/2, so the exponent here is slightly larger than that. And then if one, for example, scales the interaction, the momenta in the interaction, then one sees that just by scaling the interaction scales to 0, so it's an irrelevant perturbation. Okay, now one word about this notation, A star of G and A of G. This means the integral, the formal integral of the creation operator against this function g of k. Actually, it's rather defining a star of k than defining a star of g, but let me skip that. What is important, however, and I would like to stress this, is that the diagonal of the interaction matrix M is assumed to be 0, so there are no self-interactions here in this model. It's a reasonable assumption, but it will be mathematically important, what I'm going to say. Okay, so what is it that we want to study in this model? Well, as I said, we are studying the Schrödinger equation. So the solution of Schrödinger's equation is given by the evolution operator, the propagator e to the minus ithg applied to the initial value of the Schrödinger equation psi 0, and that gives the solution at time t. And here I want, however, to switch to a dilated Hamiltonian. So I do not study the unitary group generated by the self-adjoint operator hg, but rather I study the semigroup, namely the semigroup generated by a dilated Hamiltonian hg of theta. And theta is here a complex, I mean it's a real parameter, but it enters the definition of hg of theta in such a way that hg of theta becomes non-self-adjoint if theta is non-zero. Yet hg of theta defines an analytic family, so all the Hamiltonians are related to one another by being an forming an analytic family with the original Hamiltonian hg being the operator for theta equals 0. Okay, so the reason for changing from the Hamiltonian, switching from the Hamiltonian to this non-self-adjoint generator of a semigroup is perhaps more mathematical than physical. Of course, eventually we want to solve the Schrödinger equation as it is up here. But this dilated Hamiltonian is a convenient tool to get this task done. And I will tell you why in a moment. So here is a fairly explicit form of this dilated Hamiltonian. The atomic part remains unchanged, but the photon energy the continuous spectra of the photon energies are tilted into the lower half plane. I'll show you a picture on the next slide. And then the interaction is also modified in a way such that everything altogether is an analytic family in the sense of Kato. So that means that the resolvent, for example, of this operator is depends analytically as an Banach space valued function on theta. Now let me what did I want to say here? No, that's fine. Okay, so let me discuss, before I come to the full interacting model, let me discuss the dilated Hamiltonian in the case that the systems are not coupled to one another, the atom and the photon field. So let's just take G equal to 0. Then the atomic energy here for L equal 2 has just 2 levels. Here they are. And then the photon energy is added to these 2 levels. And it's a mathematical fact that if you have an operator of this structure, so with one operator on the left factor of the tensor product acting and one on the right, then the spectrum of the sum is the sum of the spectra in a set theoretic sense. Here it would actually be the closure of the set, but this turns out to be a closed set right away. So the spectrum of the non-interacting but dilated Hamiltonian, sigma of H0 of theta, is therefore the union of half rays, half axes pointing into the lower half plane emanating from these energies E0L. So let's look at this in a picture. So for L equal 2, the situation is as follows. We have two energy values, 2 atomic energies. So here is E1, where the subscript, 1, 0, and here is E2, 0, and when we look at the spectrum of the Hamiltonian with theta equals 0, so the original non-interacting Hamiltonian, then the spectrum is real, and so the continua that we attach to these eigenvalues would just cover the real axis, and it would be very difficult to analyze this eigenvalue, this excited atomic eigenvalue, because it is embedded in the continuum that emanates here from E1, 0. We want to uncover this. We want to study, so to say, the singular nature only that comes from the continuum starting here at E2, 0 at this excited eigenvalue, and we can do this by using this complex dilation. And the complex dilation has the effect that, think of these pens that I'm holding up here as being the continua, one attached to E2, 0 and one to E1, 0. And when theta is equal 0, that's the situation I'm displaying right now. When theta is positive, then these tilt down here, and the angle between these rays, these pens, and the real axis is roughly equal to theta for small theta. All right, so then this is how the picture I'm showing here comes about. And when we switch on the perturbation, then the picture changes to this. So I have drawn here in light circles, the previous eigenvalues are these were the positions where the eigenvalues were before, and when we switch on the interaction, then the ground state energy, the lowest spectral point of the system, will move down, but stay on the real axis. Here it is, and from the real axis there is the spectrum is still pointing into the lower half plane at a certain angle, but it is contained in a conical domain, as I indicated here. We don't precisely know, in fact, what it looks like. One could improve this cone to a cusp, but let's just leave it to a cone for the moment. Okay, so that's the ground state energy, and the excited atomic energy moves into the lower half plane, turning into a resonance. So this black dot here is an eigenvalue of the dilated interacting Hamiltonian. And the question whether these black dots are actually eigenvalues or just points in the spectrum of the dilated operator is non-trivial. So that took a lot of work to answer these questions. Having this resonance eigenvalue now in the lower half plane, and with imaginary part being of order g squared, establishes the time scale that I had just displayed here, t proportional to proportional to g inverse squared, because one knows, and from theoretical physics, from the quantum mechanics course, if you like, that the inverse of the imaginary part is the time scale of decay of this excited eigenstate. So for an interacting atom, there's only one stable state, the ground state, and if we have an excited state, it will have a finite lifetime. It will eventually decay into the ground state. This is the principle by which all solar panels and lasers and everything works. This excited state has a finite lifetime, and the lifetime can roughly be estimated to be the imaginary part here of this resonance, and which is at the order inverse square. And our research is exact. Yes?
I thought that displacement came from the theta, but no, but that...
No, the theta has just, so to say, swiveled the continua into the lower half plane.
Do these cones go down forever, or are they bounded?
No, this is just my my bad drawing. In fact, I only managed to copy this one guy here to here, but it's meaningless. This horizontal line here, it extends to all the way into minus infinity. In fact, that this goes, so to say, down forever is a source of mathematical difficulty, because otherwise, if the picture was like this, then one could draw close contours around the spectrum, and then one would have a very complete and nice picture of the dynamics, by Cauchy's integral, basically.
Sorry,
yes.
Follow up on John's question. The distance between of the second black dot to the real axis. It depends on g and on theta?
No.
No, it's in fact.
If theta was 0, it would still
yes.
lie below.
It would stay there. Yeah, that's a good point. This is, so to say, a fact from complex analysis. If you have if this is the interacting, the resonance eigenvalue, e.g. G02, and here is this black bullet EG1, then these numbers are independent of theta, and they're locally independent of theta. So let me just take this rod here to indicate that you will only see them. I mean, they only become visible as theta is so large that they be uncovered. So actually, we have here a projection of the Riemann surface related to the resolvent matrix elements, and we want to uncover these singularities on the second Riemann sheet. And theta is a parameter that parametrizes the projection onto a complex plane. And so think of this as a sheet of like a carpet that I now move down, and then I can see the spot here under the carpet. Okay, so let's go on. So this, I have now put up a slide here about the things that I told you here in the picture on the past slide, with a slightly more higher mathematical precision. So this is a result that for the model I have just described can be found in the paper by Fröhlich, Siegel, and myself from 20 years ago. And in a more singular case, for mu equals 0, it was established, I mean, let's say with the biggest generality by Jana Reka this year in a very nice master thesis. Unfortunately, Jana Reka left mathematical physics and is working in stochastics now. So the spectrum, what we know about these models, I mean, not only in a drawing, but in formulae, more precisely, is the spectrum of this dilated Hamiltonian is contained in a union of cones. So C is a cone whose tip is ELG, as I had indicated, and the cone is tilted by an angle by by roughly theta, angle theta. And these tips of the cone, they are actually eigenvalues of the operator, and their position can be computed. So it turns out that all these interacting eigenvalues are, as G tends to 0, continuous in G. They tend to the original unperturbed eigenvalue. And in fact, for the excited eigenvalues, so for little l bigger or equal than 2, so 1 is the ground state energy, and 2, 3, 4 are the excited levels. For these, the imaginary part is under a certain generic assumption, genericity assumption. The imaginary part is a constant depending on the level times the coupling constant square plus small order corrections. And here is the cone that I described. Its opening angle goes to 0 as the coupling constant tends to 0. So, and this picture here is established by applying the renormalization group based on the Feshbach-Schur map. Okay, so but this is, so to say, the starting point of what I want to study. My goal and of our group, Jacob Möller and Matthias Westrich, was to study the propagator and to find approximations to the propagator in terms of effective generators. Let me just draw the cones here once again to the picture. So, so for this dilated generator, we can write the propagator, the semigroup that generates it, in terms of a contour integral. This is a Laplace transform, if you like, what I have given here for positive times. This is all for positive times. And then I can I define in the line below an approximate propagator at level L for time t, and this is so to say the part of the integral here of this contour integral. This contour integral runs along just above the positive real axis, and let me just indicate this here. Maybe I can take away these numbers. So just above the real axis, we have the original contour with an I epsilon, and epsilon is taken arbitrarily small. And then I can separate the pieces in the vicinity of each of the eigenvalues, and these pieces of the contour I call UL. And then we prove the following statements. The first statement is kind of a setup lemma. It says that the propagator is dominated by the contributions from these parts of the contour that are in close to each of the eigenvalues. So basically it says, this lemma says we can forget about all these parts. This is not the way it's technically done, but what we do is we bend the contour down into the lower half plane, like this. And then all parts that I draw green now, so they're well below all the, the imaginary part is in magnitude bigger than the biggest distance of a resonance energy from the real axis. These green parts of the contour can just be thrown away. They don't contribute to the propagator, only with a negligible contribution. So now we study the sum of these propagators UL of t. And our main theorem is a statement about each of these UL. Okay, so here's the main theorem. So what it says is the following: fix an energy level, little l, then corresponding to this energy level, the propagator UL of t can be, for any time scale t, the propagator can be approximated by a fixed operator AL, then a time-dependent part which has the form of a semigroup, and then again on the right some other fixed operator BL. And the approximation is accurate. Now let's look at the error term first. The approximation is accurate up to the exponential time scale given by the imaginary part of the resonance. And then there's a decaying piece, t to the minus p. So in some sense, the most important part is this guy here. Because the contribution itself, so if I ask how good is this estimate, then if I write down, there are a few parentheses missing here. If I write down the contribution, this contribution here to the propagator, this approximation, if I write it down and estimate its norm, then this is at least a small constant times this exponentially decaying factor here. Yeah, so the relative error is t to the minus p. Okay, so let me come to this exponent that enters the semigroup here. The exponent is of the form the resonance energy, which is acts like a fixed eigenvalue in this evolution in the semigroup, plus one particle energy, a function TL into which the photon energy enters as a function. So this is defined by the functional calculus. I have a C1 function T, and into this C1 function capital T I plug in the field energy as an operator, and this function is very complicated, but roughly speaking, for small energies it is asymptotically equal to the identity. So up to small corrections, this guy here, this function is basically h photon. So if I now relate this term to the picture, then so e to the L G is such a resonant eigenvalue. Here's the real axis again. Yeah, so it's not related to the picture above here. So here's the resonance eigenvalue, and then there is a function which is asymptotically equal to a straight line with an angle theta, and this is here, however, this would be so this here is the dotted line is ELG plus e to the minus I theta r. Yeah, that's the dotted line, half axis, and this solid line I'm drawing are the spectral points ELG plus e to the minus I theta times TL of r, where r is positive. Okay. So, given this picture, we consider this Hamiltonian, even though it is difficult to compute to concretely compute the capital T. We consider this a simple, effective generator of the dynamics. Simple because it's just a function of the photon energy operator. Okay, so let me discuss this result. The statement of the theorem, when we study timescales of order, which are big compared to G inverse square, but not too big. In fact, if they are of the order t times logarithmically growing in G factor compared to G inverse square, this statement of the theory is well known. For isolated eigenvalues, it was known long before. can be found in Reed-Simon, for instance. But in the context of these field theoretic models, it was studied only 20 years ago. Again, Fröhlich-Siegel and myself did some work on this. Matthias Mück had an important contribution in his diploma thesis. And a very nice and complete analysis was given by Hassler, Herbst, and Huber in 2008. And then there were also other groups that had formulated sharper versions of this time estimate. So, for example, if we study atomic resonance curves, then I think the paper of Hunziker from 1990 is still the best work in that direction. And then there's, however, also an important contribution by Klein, Rama, Juliane Rama, and Wüst from 2007. And Klein and Rama have actually also studied a model of the type I'm discussing here, the spin-boson type. And they, however, aim at a different type of decay estimate, namely the type of decay they obtain is of Gevrey type. So that means the time dependence of their decay estimate is with a pretty good constant, but the exponent of that enters here for t is not 1, but it's smaller than 1. Yeah? So it's not exponential, but it's less than that. Okay, our proof uses the renormalization group mapped on this, not mapped, based on the smooth Feshbach-Schur map. This approach was developed in Chen, Fröhlich-Siegel, and myself again some 15 years ago. And I will indicate in a picture what we actually do here in a moment. Let me, however, point out one detail that I mean, is sort of to appreciate the decay estimate. We had for a long time we had struggled with the question: is our estimate, our error estimate, good at all? I mean, is the error not bigger than the quantity we want to estimate? Yeah, everybody who does estimates knows this can easily happen. And so do we get a non-trivial result? And it turned out that we got a positive answer to that question only by really very carefully choosing the parameters in the renormalization group scheme. So the renormalization group scheme that we are using is, like many others, is one which is discrete. It goes in discrete steps, and there is from one scale to the next scale there in the change of momenta there's a scale parameter. Our scale parameter is called rho. So so in the nth step, in other words, we look at momenta with magnitude between rho to the n plus 1 and rho to the n. And there's some freedom. I mean, rho is a kind of an arbitrary mathematical parameter, and there's some freedom in the choice. And we are using this freedom because when we want to get an estimate here which decays like t to the minus p, we have to choose the rho. I mean, first we have to fix the t we want to look at, and then we choose rho so that rho times t is an integer. Yeah? And if we choose it in a way that it is, for example, a half integer, then the error estimates are very bad. I mean, at least the ones that we get, and if we, compute the result, we don't get this error bound here. Okay, so let me also make another remark, namely we are approximating here UL with this operator, each UL, but what we are interested in, we see this here in the previous slide, what we are interested in ultimately is the full propagator, and the full propagator is the sum of these UL, these single contributions. And we know a priori that the contribution for L equal 1 is not going to decay at all, because for L equal 1 we are studying the propagator here in the vicinity of the ground state energy, and there's no decay of that one. So the object we are studying here, this propagator UL, and the fine UL and the fine estimate on UL does not imply that we prove a decay of the semigroup here. Yeah, it must not decay. I mean, it has a bound state. All right. So in the end, I would just want to in terms of a drawing, indicate what we are actually doing here. So let me just focus on say E2 of G, and up here is the real axis. In fact, it's very far up. I'm only drawing it here, so because the blackboard would otherwise not be sufficient, but really I'm zooming in to a small vicinity of this eigenvalue, and the real axis is on the moon or something like that. Anyway, then there were the pieces of the contour that were irrelevant. We throw them away. So these were here's the cone. Let me draw the cone. So this cone we know contains spectrum, and we must not touch it with our contour. So what we do is we let these unimportant pieces of the contour, we take them out. These are the green pieces. So there is a contour that comes, so to say, from down here and goes to the right into the lower half plane here to the next eigenvalue, possibly, if there is a higher eigenvalue. And the interesting part is what do we do in between. And here we have the shells of energies that come from the renormalization group. So this is like an onion layer by layer. So let me draw not too many layers, maybe just 3. Of course there are very many, and this is already not so good. A bit more space, and then the relevant layer, let's say, I want to focus on is this third one. And then so then we basically construct the contour piece by piece here from one layer to the next. And in the last step, we choose a special contour, because we know we have to close the contour above the resonance energy. So this potentially gives rise to an exponentially increasing or less rapidly decaying part of the contour. So what we do here is it's chosen in this way. It goes up here, then it almost touches the resonance energy, and then it goes down here. So like that. And the distance from between the resonance energy and this upper part of the contour, the distance is by 1 power of the scale parameter smaller than the radius given here. So this upper part of the contour is very close to the resonance eigenvalue. And then what we do is we approximate, then the renormalization sets in and tells us the interaction after these n renormalization steps. The remaining interaction is very complicated but small, because we have a model with an irrelevant interaction. So we just basically throw it away and approximate then in the last step the effective Hamiltonian by just the free part without any interaction, and estimate the error made. And this is going to be small then. So that's, in rough terms, the strategy. I'm sure that those of you who are familiar with the renormalization group have now a pretty good idea of what this means in practical terms. Thank you for your attention.
Thank you very much for a nice talk. Do we have questions?
I got confused about the theta dependence again.
Mm-hmm.
In this estimate you have a theta in the denominator. So how uniform is it in theta?
It's non-uniform. Mm-hmm.
Or can you use analytic continuation?
Locally.
Locally only.
Jörg.
I guess if you look at matrix elements in dilatation analytic vectors, you can undo the theta, I guess. But only for matrix elements.
Not for these.
It has to blow up, because it just reflects that we are doing that we are, so to say, going over the spectrum with the spectral parameters.
Theta to be big enough so that you can. You said the irrelevant parts are below the lowest of the resonances. So if the wedge is too far and.
Yes. So there's an order here. Theta is small, but once theta is fixed, it's fixed. And then G, the coupling constant, is even smaller.
Well, I was a little bit unclear about the role of rho. I think of it as a regulator, right? But if you put in a regulator, why not just cut off all the low momenta entirely, and then you wouldn't need a renormalization group? So what am I missing here?
This we can do, but you have to get to the scale where you cut off the remaining momenta entirely, and for that we need the renormalization group, if I understand the question correctly.
Well, but that presupposes that there's some true model, right, with that you're trying to get at, which has zero momentum modes, right? But
a true model without interaction, yeah. But it.
So yeah. So what is the model you're after?
So I'm asking, can I describe the evolution by a Hamiltonian that is a function of the field energy only, in the vicinity of zero field energy? So then it's plausible that it should be asymptotically, as energy goes to zero, it should be proportional to the field energy. To first order, we have it's a small perturbation of the field energy. And then there are corrections, and what I'm claiming is we can take these corrections into account and get an effective Hamiltonian for small energies. Tom, you also?
Yeah, no, I see that the Van Hove time scale is g to the minus 2.
Mm-hmm.
But so what time scale can you get at all time scales?
Any time scale,
any time scale,
but not t infinity. You have to choose a large but finite time scale. So it's not scattering theory that we are doing. Mm-hmm.
maybe in the interest of the audience, one might add that there is an alternative approach to these questions, which was developed by Wojciech Deruk, Antti Kupiainen, and maybe also a little-known theorist from elsewhere, which is also based on renormalization group ideas and does not require any complex dilatations. So you seem to have some difficulties in recovering those results.
Mm-hmm.
This particular approach. Maybe Antti can comment more about that.
I'm not sure I want to comment more about it. I mean, you know, as well as me, that in that case, I mean, the really interesting problem was not actually being able to do with a renormalization group either.
Other comments?
But we can do a comparison. I mean, this well-known physicist and Antti and Wojtek is not here, is he? Oh. Should be subject to discussion.
For example, shows that you relax to the ground state in this situation.
Yes.
If you look at any sort of local observable and you ask how does its expectation behave for large time, given essentially any initial state, it starts to look like the expectation of the ground state.
Yeah, that's right, sure.
It can also be done by scattering theory, but then you have to do some asymptotic completeness, which could be difficult to do.
Excuse me. Could you be a little bit more precise about the statement for theta equals 0? So what do you get for as an estimate for the finite time behavior at time t for hg at theta equals 0?
Mm-hmm.
What do you get?
Okay, so
how much does it depend on the order of magnitude of t also? Because it's not uniform in t, as you said. It's not scattering theory. So I would like to understand the dependence in t of your estimates.
yes, so I mean, once the theta is chosen and g is fixed, t is free to choose. Yeah, I mean, the constants do not depend on t here. Okay. Now about the theta dependence. For example, as Jörg pointed out, you can compute matrix elements for dilation analytic vectors. One which is here in this model available is the vacuum vector. So one can immediately compute and estimate the matrix elements of 0 photon states into 0 photon states, yeah? Which may or may not be so interesting. I don't know. I mean, depends on. And the theta dependence there, I mean, that's a good. I mean, of course, these estimates here are not uniform in theta going to 0, obviously not. And one has. I would have to carry out the computation and see that it drops out, yeah, that one gets a result that where the theta is actually oh wait, no, it's theta independent. What you get there for the vacuum vector, for example, is just theta independent, yeah. It's not only analytic, it's independent in theta, so that's the result, yes. Mm-hmm.
The most interesting quantities to compute are theta independent or covariant or anything.
Well, analytic in theta. The vectors that this can be applied to are those that are analytic in theta, not necessarily constant.
So can you take the limit theta goes to 0 then?
No, but if it's theta independent, then I can.
Yeah.
Mm-hmm. So that's so to say, an fortunate accident. So the practical use of these dilated generators is questionable. Yeah, I mean, Yeah, let's say so.
I think, I mean, it gives good information about survival probabilities. You look, if you start with a state that is close to one of these excited states, you ask how long does it survive, this you can compute with these estimates.
Mm-hmm. That's right.
In the choice of this contour here, I understood it as meaning that you want a union of horizontal and vertical lines which stays away from the wedge.
That's right.
But the top line goes quite close to the.
That's right.
Are you trying? I mean, you cannot compute the residue of this or something exactly from the top, or not.
No, only if we, so to say, throw away parts of the model here so that it becomes an isolated singularity. Otherwise, no. Yeah. So one way of doing is to introduce an infrared cutoff to the model. Then this little piece here becomes free of spectrum. I mean, that's one way to go. It's not our way to proceed, but this is one possibility. And to make this resonance then an isolated eigenvalue then by this procedure, and to show that the interaction that is and the part of the free energy that I mean the free photon energy that I'm throwing away by taking out this part is negligible. And then indeed one can close the contour below the resonance and compute the contribution from the residue.
Questions or comments? If not, then I guess it's time for lunch. And thank you again.
Thank you very much.